Hi, ladies and gentlemen. Thank you for your time attending my presentation at the 2021 China Semiconductor Industry Association ICCAD. This year, I'm going to present how you could achieve maximizing SoC bandwidth using dynamic voltage and frequency scaling. In this talk, we will introduce two new kinds of products that have been made as second questions for ultra-fast DVFS and talk about some difficult problems that can be solved with these new products. We have been providing clocking IPs to our fabless IC customers since 2006 and have been growing consistently since 2010. As you can see from the graphic of customers by region and year. We have development design center in Atlanta, USA, and Krakow, Poland, and our customers' chips using our IP are in volume production from 180 nanometer down to 5 nanometer FinFET. Our 3 nanometer peers are second proven already. Our design engineer understand their main mission is to help our customer to get to market quickly, and our quality and support has been recognized with multiple Best of Awards, including Best AMS from TSMC for the past 5 years. We are also ISO 9001 certificate, which is appreciated by our customers in making automotive chips. SerDes is one of our key product lines, and we focus primarily on the PMA, the high-speed analog power, including the serializer, line driver, line receiver, equation, CDR, and digitization. Our peers have enabled extremely good performance in the micro-semi FPGA and also very low power. Over the past few years, we've ported and proven this multi-protocol PMA to a number of mainline process nodes. In addition to our multi-protocol PMA, we have protocol-specific PMAs before V-by-1, DisplayPort, JESD, APD-Link, and several customer interface, as well as ultra-low latency PMAs. Around half of our revenue still comes from POs. The core of this business is the general-purpose virtual synthesizer that is so widely programmable. We have used in hundreds of chips and a wide variety of markets. This has resulted in some truly gigantic volume. For example, in TSMC 28 nanometer, over 140 production chips use this IP, and in 12-16 nanometer, over 50 chips use it. This has resulted in many millions of wafers delivered to customers with our POIP. These kinds of volume are a testament to our robust, high-yield design and customer support. We've leveraged this high-volume design to make PO variants that are optimized for low jitter, extremely low power, and discrete clean-up POs for the cadence DDR5s. Our 3 nanometer silicon is being tested now, and its performance matches simulation. Now, we will introduce you to a new IP, a frequency generator or frequency lock loop, that is capable of switching frequencies within a few nanoseconds, making it ideally to new kinds of applications. First, though, we are going to talk about why designers using dynamic frequency scaling. The matrix on the right-hand side shows how logical speed varies with process, voltage, and temperature. The variation is gigantic, 2.5 times over normal voltage range, and up to 10x over the extended range commonly used in modern SoC, and especially in HP compute chips and AI accelerators. Because we must meet logic timing for the worst case, most chips in production are performed well below their potential speed. We show the supply voltage on the horizontal axis of the tables, and it's obvious this effect dominates. This means that even if chips are being into fast parts and slow parts, and the supply voltage is adjusted accordingly, dynamic change in the supply voltage must be accounted for by allowing more timing margin. If we can adjust the clock rate as the power supply level changes, the chips can run faster when the supply is higher and slower when the supply drops. We have built a new product that is designed specific to generate the clock needed in the situation where the supply voltage changes rapidly. It's called a frequency generator. We built this product from the proven Fisher PL, so it's a low-risk derivative. We took the copy of that PL VCO current and passed that through a DAC to drive the copy of the VCO. This provides a second output, which is the frequency lag to a fractional multiple of the reference clock, and that can be programmed over 2.5 to 1 frequency range before an asynchronous output divider. We designed the DAC to be asynchronous, programmable, and settle quickly without an overshoot. While PLs initially settle on timescale of a millisecond, and because they are higher order loop, they either overshoot or settle very slowly. The DAC does not overshoot at all or settle on a timescale of 12 nanoseconds. This enables DFS with a smaller timing margin and with a frequency range 50x or to 100x faster than before. The frequency switching is even fast enough to detect a supply glitch and drop the large clock ahead of the supply drop. As you all know, transistors in the most advanced process do not match very well. This means the output of the VCO2 will not be perfectly on target. In this design, the copy can have a frequency error in the range of 2%. To deal with this, we have added a slow digital calibration loop that adjusted the DAC control so that the actual ratio of the two VCO output frequency matches the programmable ratio. Once the calibration is complete, the calibrated DAC control work can be read out, stored in a lookup table in non-volatile memory, and used for future transition to the same frequency. With a one-point calibration, the initial error on the frequency jump is below 0.5%, and with multiple calibration points can be better than 0.01%. We can perform this calibration on a production test or on the first boot of the system. We developed our first FG in 5 nanometer, and this slide shows some measurements with the DAC program to have the output switch from 1.6 GHz to 3.2 GHz and back. You can see the output clock divide down to 800 MHz to get it off chip. Transition rapidly and smoothly to the target frequency without glitch or overshoot. The steps are an artificial or updating the frequency after each clock period measured. The equivalent time constant we measure here is around 7 nanoseconds, which is likely faster than a supply drop in a chip with acceptable on-die decoupling. Now, we will take a closer look at the application for the frequency generator and introduce a companion IP that we have developed. The companion IP is a new kind of circuit building block that we call a DDC. This is a delay to digital converter because the FG will be used to react to change in logical circuit timing. We believe It's better to directly sense the logic timing than detect the three factors: process, voltage, and temperature that impact timing, and attempt a complex calculation to predict what clock frequency would be acceptable. The DDC is clocked by a fixed frequency and generate an output word that represents the core logic delay at the moment of the clock. The DDC can also average this delay measurement over several clocks. The graph on the right-hand side shows how the DDC output code varies with supply voltage for different clock rates, chip process corners, and junction temperatures. As expected, the output code increased monotonically with supply voltage. The FG and DDC can be used for automatic DVFS using the simple application diagram on this slide. The fixed output frequency of VCO1 is used to clock the DDC, generating code that presents the instantaneous logic speed. This code can be input to a lookup table to generate a desired frequency ratio between the output VCO1 and VCO2. The lookup table needs to be calibrated once for each chip, and the actual lookup table values would then account for mismatch effects in the DAC, VCOs, and the DDC, as well as process corner and supply voltage effects. This will enable each chip to be calibrated to always run at the maximum possible safe frequency, no matter what the current junction, temperature, and supply voltage are. Whether the chip has been spin or not, this method enables chip designers to obtain significantly more performance without spending or needing to move to a more expensive process node. With a small addition, the DDC and FG can also enable chips to automatically adjust logic clock rate when an event outside a logic circuit causes the supply to drop. This might be something like a reset or a set of memories or starting several processors code at the same time. This kind of event can cause rapid increase in supply current, and the package of PCB inductance result in a fast supply drops. In most cases, a rapid change in the DDC code can be asynchronously detected in a digital comparator to indicate the start of such supply drop. The comparator can immediately switch the logic clock to a safe low frequency. After a short time, the circuit can switch back to the VCO2 output, which is controlled by the lookup table and the DAC. It's not necessary to have the knowledge or design for the dynamic behavior of on-die and PCB level supplies or how the package impact their dynamic behavior for each unit build. The DDC plus lookup table loop will automatically adapt in each case. Some early adopters of our solution believe that a supply glitch detector would be needed in some chips, as the supply dip would be too fast even for a DDC clock at 2 GHz. While we haven't found this to be necessary, the diagram shows how the supply voltage dip detector can provide input to the digital comparator to trigger the clock marks. Thank you for listening to our presentation. We trust it has been worth your time. We begin by giving you a high-level overview of our company and main product lines, and alert you to our 5 years of Best Award from TSMC and recent silicon success in 3 nm. Following this, we introduce you to a new kind of circuit that we call the FG, we build this IP from any of our proven version PO, but at a second output whose frequency can change over 50x time, faster than the PO can adjust, and does this without glitch or overshoot. We then introduce you to a second new kind of circuit that we call delay to digital converter, which directly measures the instantaneous logic delay. Using the DDC together with FG enables very fast DFS with response time of less than 10 nanoseconds without the need of understand and predict the complex relationship between process, voltage, and die temperature, and the resulting maximum logic speed. This pair of IP will help you to get more processing cycle out of the same design without needing to move more expensive wafer process. We think the DDC is fast enough in particular logic design to even adjust for supply glitch, but show you how you can react even faster. Once again, we thank you for your valuable time.